Hello, I'm Alex Wolski, and I'll be presenting compute shaders and how they can be used to run parallel programs. The graphics processing unit, or GPU, is a highly parallel hardware device primarily designed for 3D graphics. However, we can run any program we like on it through the use of compute shaders. In this presentation, I'll cover the advantages of a GPU, the rendering pipeline of a GPU, how GPUs are implemented hardware-wise. I'll cover the shader programs that we run on a GPU and some example usages of these shader programs. Why would we want to run our programs on a GPU? As I said before, GPUs are primarily designed for highly parallel graphics applications. These could include real-time 3D video games or heavy image processing, such as what you would use in Photoshop. And this is done through the use of hundreds or even thousands of lightweight cores running in parallel. This is in stark contrast to how a CPU is designed, which uses fewer but more powerful cores. In a traditional consumer computer, you might have 4 cores. In each core is assigned a different task or set of instructions, and these operate on different data, which makes it a multiple instruction, multiple data architecture. The issue with this system is that the parallelism is limited by the data flow. Our problem can only be separated into so many tasks before we have to wait for the results of a previous task to be done first. In addition, this requires complex scheduling algorithms in the operating system. In contrast to this, the GPU can have tens of thousands of threads in flight running on hundreds or thousands of very lightweight cores. And all of these threads are running these same tasks, making it a single instruction, multiple data architecture. And these threads are simple enough that they can be managed by the hardware on the GPU, managed and scheduled, instead of from the operating system. The highly parallel nature of a GPU also helps us avoid the power wall. As we learned in the first lecture of this class, the power consumption of a hardware device is proportional to the cube of its frequency. For a CPU and a GPU to have a similar throughput, the CPU would need to be clocked at a higher frequency since it only has 4 cores. This would exponentially increase its power consumption. The GPU, on the other hand, has many more cores, so it can run at a lower frequency, but because of the heavy parallelism, it can still achieve the same throughput. Lastly, GPUs are appealing for their cheap price. GPUs aren't the only specialty parallel processing devices. In the early 2000s, field programmable gate arrays and cell microprocessors were also very popular. However, they lost out to the GPU over time due to price. GPUs had a high demand from the entertainment industry, specifically video games, so the price went down. The rendering pipeline is a high-level view of how data flows through the GPU. It is not 100% representative of how the hardware is implemented, but the two are closely related. The job of this GPU is to take a number of 3D points, vertices, and polygons connecting these vertices and convert those into an image on the screen. The first step in the pipeline is the vertex shader. This takes the vertices, which are in the world coordinates of the scene, and converts them into local coordinates of the camera. Then the color of each vertex is calculated depending on the number of light sources in the scene and their locations. The rasterization phase takes the vertices and triangles and converts them into fragments, which are essentially pixels with some extra information. The pixel shader, also known as the fragment shader, manipulates the rasterized fragments. In this case, an image is being applied to the fragments to give them more detail. The Z and alpha phase manages the transparency of fragments and makes sure that the fragments overlap each other in the correct manner. After this, the resulting fragments are written to a buffer, which is then sent to your display to be displayed. The stages in green are programmable, which means we as developers can write a custom program to define the behavior during these stages. The stages in red are fixed functions, meaning we can configure how they work, but we cannot rewrite the program. This is done to improve hardware efficiency. Most modern GPUs use a unified shader model. This means that the vertex shader and fragment shader stages, these two in green, are combined into a unified shader stage. On the first pass, the vertex shader program will be executed, then rasterization, and on the second pass, the fragment shader program will be executed before moving on to the Z and alpha and frame buffer stages. So how is this pipeline implemented in the hardware? To explain that, we will be looking at the AMD Radeon HD 7970 GPU. In this GPU, there are 32 compute units, and each compute unit has 4 single instruction multiple data engines inside of it. And each of these 4 SIMD engines has a 16 vector ALUs. Each of the colors here represents a different instruction. So all 16 ALUs in each of these SIMD engines is running the same instruction. But the SIMD engines are running different instructions. This essentially means for each of these 32 compute units, there are 4 cores inside of it running different instructions. So we can have 128 different instructions running simultaneously. In this manner, the GPU is a combination of the MIMD and SIMD architectures. Each of the 4 SIMD engines here will execute its own thread, and each one has its own 64 kilobyte register file. The 4 threads on these SIMD engines can communicate with each other through the shared level 1 cache. And all of the compute units can communicate with each other through the level 2 cache, which operates very similar to a CPU cache. It retrieves data from the main GPU system memory, the DRAM, in cache lines, and stores it here. All GPUs won't have this same architecture, but it will generally be fairly similar. Here is the NVIDIA Fermi architecture, which came out around the same era, and has a similar layout. Instead of compute units, NVIDIA calls the higher level cores streaming multiprocessors, and inside of each of these multiprocessors is a CUDA core, which is analogous to the SIMD engine from the AMD architecture. One important distinction between the architectures is the register file. In the AMD architecture, each SIMD engine had its own private register file, but in the NVIDIA architecture, the register file is shared between all of the CUDA cores. And the number of threads in flight actually determines how many registers each thread is allocated. So it is possible, if you have too many threads, that each thread will have too few registers and performance will be decreased. The threads are organized in a manner to fit the architecture of the GPU. A single thread will run on a single SIMD engine in the case of the AMD architecture, and it has its own private local memory. Each compute unit will have a block of threads, all which have a shared memory, and the entire GPU will consist of a grid of threads. Same as with on the CPU, the GPU experiences hazards. One of the most common is the stall hazard. On a GPU core, say we are executing a thread, and then it performs an I/O operation to system memory. Although the GPU DRAM is much faster than the CPU system memory, it still takes about 40 to 50 clock cycles for the data to come back. So during this time, this thread will stall. Instead of letting the hardware stay idle, we can start executing the next thread until that stalls, and execute the next thread, and so on, to try to keep the utilization of our vector ALUs close to 100%. In order to completely hide this memory latency, we want enough threads that we can keep executing until the first stalling thread finishes its I/O operation and is ready to execute again. The way the GPU core switches between threads is very reminiscent of Intel's hyperthreading technology, but in the GPU, the switching of threads is much quicker, and we have less overhead. One of the disadvantages of this single instruction, multiple data architecture is that we lose performance during branches. We have multiple threads running the same instructions, and they're performing the same operations. If we get to a conditional branch, some of the threads may take the branch and some of them may not. In this case, the 3 yellow threads are executing the first code block, and the 5 gray threads are executing the second code block. But we can't tell the yellow threads to continue on the operation and skip the second code block. Likewise, we can't tell these 5 gray threads to skip the first code block. Because they're all being fed the same instructions, they all have to compute these operations, even if they're not useful calculations, and we're going to disregard the output from that anyway. In this particular example, we have about a 0.5 times slowdown because each thread is executing about twice as many instructions as it needs to. But in the worst case scenario, we could have 8 possible outcomes of this branch, and each thread would execute all 8 outcomes, which would result in a worst case of a 1 out of 8 peak performance. One way to avoid this situation would be to group the threads based on which branch they take. If all of the threads on GPU core take the same branch, then it won't need to execute the other code blocks that don't get reached. Now that we understand how GPUs work, we can start writing programs for it. These come in the form of shader programs. Our application could be, a game engine or animation software. Whatever our host application is, we'll send a shader program source file to a graphics API. This API, most APIs will compile this down to an intermediate language, a high-level shader language, which is then sent to the graphics driver. This driver is going to be specific to the hardware you have installed on your system, and it takes the high-level shader program and compiles it down to binary that can be executed on the GPU. This is then sent to the GPU along with any other data that is required and processed. An important aspect of shader programs is that it doesn't contain any explicit parallel programming. If we are creating a vertex shader, then the program will be run on every vertex. Or if we are running a fragment shader, then the shader is run on every fragment. We don't need to bother with the communication and synchronization between threads. However, this may be necessary for certain applications, especially in compute shaders, because we can run into race conditions. There are many different graphics APIs you can use, all of which use different languages. These are the most common 6. Vulkan, OpenGL, DirectX, and Metal are geared toward real-time 3D graphics, while NVIDIA, CUDA, and OpenCL are more geared toward general parallel processing applications. Metal is Apple's API, which only works on Macs. DirectX only works on Windows, and OpenGL and Vulkan are cross-platform, as well as CUDA and OpenCL. CUDA and OpenCL aren't specific to the graphics card. They also compile for CPUs and other hardware. And these two don't contain compute shaders. The other four, Vulkan, OpenGL, DirectX, and Metal, all have their own but different version of compute shaders. If we have a general parallel program disconnected from 3D rendering and graphics, why would we choose one of the graphics APIs geared toward 3D graphics instead of CUDA or OpenCL? Both CUDA and OpenCL are designed for heavyweight parallel processing applications. Well, the performance of a compute shader on one of the 3D graphics tuned APIs may perform better. This is a simulation of light particles passing through a transparent medium. These, on the x-axis, we have different numbers of threads. So starting at 512 threads going all the way down to 128. And as we would expect, the performance goes down with the fewer number of threads because we're reducing the parallelism. And this is on 3 different models. And the y-axis is the time it took to run the simulation in frames. So the higher, the longer it took, the lower, the better. And in all 3 of these cases, the compute shader was either the fastest or tied for the fastest implementation of the algorithm. The fragment shader was, arguably the worst, with OpenCL lagging behind. CUDA is fairly close to performance in the with the compute shader, but it marginally loses out. And one of the reasons for this is because OpenGL, which was the graphics API used in the simulation, is much more mature and is a bit more optimized for the GPU than OpenCL or CUDA, which aren't specific to the GPU. In general, there are 3 different types of shader programs: the vertex shader, fragment shader, and compute shader. The vertex and fragment shaders correspond to their respective stages in the rendering pipeline. The vertex shader programs the behavior during the vertex stage, and similarly, the fragment shader programs the behavior during the pixel/fragment stage. These are linked with the graphics pipeline. But the compute shader is independent. It relies on the same unified shader processor cores that the vertex and fragment shader uses, but it's not restricted by the different stages of the rendering pipeline. The code of a compute shader is very similar to that of a vertex or fragment shader. The main difference is the inputs and outputs to and from the shader. To close out the presentation, let's look at some examples of compute shaders in action. So here is an example using collision detection in the Unity game engine. Using just the CPU and the built-in collision detection system, we get pretty abysmal performance. This is rendering less than 3 frames per second. And using the compute shader, get a much smoother result with over 34 frames per second, which is over a 10 times performance increase. Another example is a cloth simulation. This piece of cloth is modeled as several thousand different mass points, which influences the points around it and acts as sort of a mass and spring system. And we can see on the CPU, as we increase the number of mass points, the execution time increases exponentially. But for the compute shader, it remains relatively low throughout. In addition to the collision detection and cloth simulation examples, compute shaders could also be used for fluid simulation or ray tracing rendering within the 3D graphics realm, and artificial intelligence and protein simulations outside of the 3D graphics realm. Here are some of the references I used for this presentation. Thank you.